Welcome. And in this video, we're going to cover Chapter 11, Network Performance and Recovery. All right. In network management, we access, monitor, and maintain all our networks. Right. It can include controlling user access, checking for hardware faults, ensuring optimizing our quality of service for critical applications. Prioritizing service like voice services, things that are sensitive to time and or quality of network. Maintaining our records and determining what time of day is best for upgrading a router, server, or application. Right, with our goal is to enhance our efficiency and performance, prevent costly downtimes and any losses, and predict problems before they occur. So one way we do this is with monitoring tools. You can have a network monitor, a tool that continually monitors network traffic, a protocol analyzer, a tool that can monitor traffic at the specific interface between a server or client and the network. And I say the difference is a network monitor can monitor traffic that a single device encounters, and that's actually the protocol analyzer, and can monitor traffic patterns throughout a particular network is the network monitor. So here we have different ways of monitoring, right? So we have a wireless monitoring going on with this laptop is put into promiscuous mode, which means it can see everything that goes across the access point. And so it's looking at all the traffic on this access point. Here we have a network tap. It's a device that's put in between two other devices, right? So the router is connected to the tap and the tap to the switch, so that all the traffic between the router and switch go through this network tap, which then is sent to this monitoring device here. It detects all the traffic between the router and the switch. On the switch, we have a port that we plug into this port, and we mirror a port on the switch, right? So whatever traffic is on the port we see, it gets copied to our port, and then we are able to monitor it here. Or we have a protocol analyzer that detects only the traffic addressed to this computer. It's installed on this computer, and whatever's coming to there, it sees. All right, and this is just saying, we have wireless monitoring. You run software on the computer connected to the wireless network, and so you monitor the wireless area network by running the software. Port mirroring, right? You're copying all the traffic on any port on a switch it's sent and mirrored to the port that you plug into to monitor from, so you're not impacting the port with the traffic. It's just copying the traffic. And then inline monitoring, you install a device. It's called a network tap, a test access point, or packet sniffer. You put it in line, you put it in between, so all the traffic goes through that device. It's called inline monitoring. All networking monitoring tools can perform the following functions, right? You set the NIC to run in promiscuous mode, pass all traffic, because otherwise the network card is designed by default to disregard any traffic not addressed to it, right? So, but you put it in promiscuous mode and it accepts all traffic, and looks at all traffic, including the traffic that's not addressed to the card. You can continuously monitor the network traffic on a segment. You can capture the data transmitted on a segment. You can capture the frames sent to or from a specific node. You can reproduce network conditions by transmitting a selected amount and type of data, so you can resend the data. You can generate statistics about network activity. So some tools can also perform the following functions, right? They can discover all network nodes, all devices on a segment, establish a baseline, including performance, utilization rate, and so on, right? This is good, that you would want to do for preemptive tasks, something before you need it, right? You want to set a baseline on what your network normally look like, right? Set a baseline so that when you're having slow performance, you can know for sure that, well, that's not what it normally looks like. What's different? What are we seeing that's different? You have a baseline to compare to. So that's a good feature to have in a network monitoring tool. Track utilization of network resources and device resources and report it in graphs or charts. So this is a nice way of displaying it graphically, what's going on your network. It's kind of a nice feature, especially for management, things like that. They like to see graphs and charts, better than just raw data. You can store traffic data and generate reports, so you can save what you captured and then generate reports from it later. Trigger alarms for certain pre-configured conditions, so you're looking for certain things and you can get alerted to whenever they occur on your network. You can even have it do something too, but open up a ticket or notify a certain work group or something. And then identify usage anomalies such as top talkers or top listeners, right? Who's the chattiest, who's using the most bandwidth, or who's listening the most, or right? Somebody that may not be right, somebody in promiscuous mode, right? Somebody that shouldn't be there. And the tools can help you find all kinds of anomalies or issues with your network, runs, giants, ghosts, packet loss, discarded packets, interface resets, but all kinds of things. And they also can help you troubleshoot. Actually seeing, did the packet get there? Did it send the request? Did it not? You can actually see it on the network. And alerts might be transmitted by email or text, right? So the SMS, right? You can have SMS messages. Another thing that we want on our networks is logging, right? So logs contain our recorded conditions and recognized by an operating system or device. Event log is a Windows-based computer log. It's just logs, just monitoring information from that device for that computer. And you use Event Viewer to access Windows logs, to view the logs. Syslog function is standard for generating, storing, and processing messages on Linux or Unix systems. And data is written to our system log. Syslog defines roles for each computer that participates in logging, right? You have a generator, that's the computer that's being monitored, that's creating the logs, and then a collector, the computer that gathers the event messages from generators. Linux and Unix systems, your logs, newer versions will store logs in the following location, the /var/log/messages, and then older versions and different versions, have different locations. You just have to figure out yours. Most likely it's going to be this var logs messages for newer versions of Linux, but you'll have to verify your version of Linux on where they store their system logs. Logs, you can use them for fault management. Logs keep our history. Logs must be monitored for errors or issues. And most Unix and Linux OS provide a GUI application used for viewing and filtering information. So does Windows. Other applications are available for sifting through syslog data and generating alerts. Yes, and there's other applications that can correlate all systems and all devices and all your logs and have a centralized location for logging. Splunk is one well-known one that does that. But then you can use an enterprise-wide network management system. You can build one using SNMP. And SNMP is a simple network management protocol. Most devices have SNMP agents available, so you can pull information from them. They use this as a message information base or something like that. It's basically the library or descriptions of everything of that device and how you can access it, and then you can have it pulled. You can pull the information over the network from each device, or you can set what are called traps, and the device can push it to the centralized location. So managed devices, any node monitored by the network management system. You have agents that collect the information, provides the information to the network management system. Right, the management information base, the MIBs, right? They contain the managed devices definitions and data. It's designed in a top-down hierarchical tree structure, just easy to maneuver and go through. Simple network management protocol, SNMP, is what is used, right? It's part of the TCP/IP suite. Typically, like I say, the management server will query and get a request from the agent and get a response. But you can also set traps. So if some event occurs on the device, it'll send information to the management server. You should be using SNMP version 3. It's the most secure version, but version 2 is still widely used, and you should, by all means, not be using version 1, right? It's not secure. Network management applications are they are flexible, challenge to configure and fine-tune especially for large complex networks, and you have to choose the correct amount of information to collect, right? Baselines, you want to create baselines of what your current operation, what does your network normally look like. The baseline utilization rate, number of users logged in per day per hour, number of protocols running on the network, any error statistics. How many errors do you normally get, and types on a regular basis, frequency of applications that are used, bandwidth utilization. And so here's an example of baseline of daily network traffic, right? By dates, so this is like for the month and a half of data, right? And it shows the utilization, right? It's pretty low on Sundays and even on Mondays. But this is just daily, showing your daily averages. So if you get a spike one way or the other, you might be able to tell something's wrong, or if it's really low, something else might be wrong. But it's good to have baselines, and not only just by date but by hour is even preferred. Then you can compare your future with past performance. Right, having your baseline data is really good. Utilization, error rate, packet drops, jitter, these are all good metrics to have right, as a baseline, so that when something goes wrong, you can say, yes, this is exceptional. This is what's going right. We're getting the high error rates, or we're getting somebody's overutilizing the network, and then maybe we can find out who that is. Right, performance, monitoring links and devices' ability to keep up with demand, whereas fault tolerance is detection and signaling of a device, the component that fails, right, that has a failure, right. So you want to make sure you have enough bandwidth and your network has enough room for growth. So that's performance management. But then you want to check and make sure your devices are all up and running, not failed state, because you may have redundancy built in, and so you may have a failed device, and you're instead of load balancing across two switches, you're actually going across one because one switch failed, right? You would find that out if you're monitoring for faults, right? The network's still going and everything's fine because it's designed. You designed it for high availability, but you had a fault or error, and if something were to happen with the remaining switch, then your network would be down, and then you would have problems. So traffic shaping, right? So this is manipulating packet data stream and connection characteristics, right? You're managing the amount of traffic traversing the network, and you're trying to assure timely delivery of the most important traffic, usually like voice, right? You're trying to prioritize, voice data over just regular data, because most of the time regular data a few seconds don't matter, whereas voice traffic matters, right? And so you want to shape the traffic and make it the best performance for all users, right? So traffic shaping can involve delaying less important traffic, right? Increasing priority of more important traffic. Limit traffic volume flow in and out of an interface during specific time periods, so like payroll period, when they're running the payroll, all other traffic items take a less priority or something like that. It could be limited monetary throughput rate for a momentarily throughput rate for an interface, right? So just slow it down a little bit. Instead of going at gigabit speeds, maybe slow it down to 100 megabit connection, while the other higher priority application runs at a gigabit, right? Right, so this is traffic volume before and after applying the limits, right? So you had the high spikes, but you cut off the spikes. You can prioritize based on protocols, IP address, user groups, differentiated services, which is a flag and IP packet, or VLAN tags, service or application. So voice over IP, video over IP are considered delay sensitive, right? So you want to prioritize them with the quality of service. You want to prevent delays, disorder, and distortion. Requires more dedicated bandwidth. The quality of service, QoS, is a group of techniques for adjusting the priority a network assigns to various types of transmissions, so we can optimize the quality of service. Improvements can be made to address the quality of services challenges, right? And we have differentiating server and COS. So QoS addresses QoS issues through traffic prioritization at layer 3. So diff-serve accounts for all network traffic. It can assign different streams, different priorities to prioritize traffic, right? IPv4 has a diff-serve field. IPv6 has a traffic class field. It has two forwarding types: expedited forwarding and assured forwarding, right? So data streams assign minimum departure rate and circumvents delays. That's expedited forwarding. Assured forwarding, data streams assign different router resource levels, prioritizes data handling, but there's no guarantee of on time or in sequence packet arrival, right? Class of service, COS, refers to techniques performed at the layer 2 on Ethernet frames. So before, right, we were diff serve, that was layer 3. This is layer 2. This is another way of prioritizing traffic. It's both often used to route Ethernet traffic between VLANs. All right, it's got a priority code point, or PCP, which is a 3-bit field in the frame header that has been tagged and addressed to a specific VLAN. And the class of service sets these bits into one of 8 levels ranging from 0 to 7. And a network's connectivity device and clients must support the same set of protocols to achieve their QoS benefits, right? So all devices need to be able to use this and speak in the class of service, right? Be able to use this frame. Networks can combine multiple QoS techniques. So availability, how consistent and reliable is a file or system, right? It's availability. How available is it? How often is it up and available? High availability refers to a system that functions reliably near all the time. Uptime, measured time functioning normal between failures, right? So how long has it been up and running, the uptime? You can use the uptime command on Linux or Unix, and there's a Microsoft utility found in Task Manager to get the uptime of a device. Typically, you're looking at servers. How long has it been up since restart? Capacity for system to continue performing despite unexpected hardware or software malfunctions. Failures, a deviation from specified system performance level. A fault, a malfunction of one system component, and can result in a failure. A fault-tolerant system is to prevent faults from progressing to failures. All right, so mean time between failures, right? You had a failure here, you had a failure here. This is the mean time between failures. This is the average amount of time that will pass between a failure, right? And the next one is to expected to occur. Mean time to repair is the average amount of time required to repair the device. Average amount of time to repair from a failure. Redundancy it helps us to protect us against faults and failures. So networks are often designed with 2 or more of the same item, services, or connections that fill the same role on the network. So if one were to fail, or have a fault, or fail, the other can take over. This allows us to have high availability. To maintain high availability, we ensure critical network elements are redundant, right? The main disadvantage of redundancy and high availability is it costs more because you have to have twice as many devices than you need just run it, because you want to ensure against a failure. So here's an example, right? The up above, you have one T1 connection, one firewall, one router, one switch, and your network is there. But it is not redundant, it is not highly available. If any one of these devices fails, your network's down. Whereas the network down below, they have 2 T1s, 2 firewalls, 2 routers, and 2 switches. So at any one time, they can lose a device or a T1 line and still function. Automatic failover is just like it sounds. It immediately assumes the duties of the identical component. Hot swappable refers to identical components that can be changed while a machine is running. So two approaches are hot spare, the duplicate component that's already installed in the device and can continue the function in case the original component fails. A cold spare, a duplicate component that's not installed but can be installed in case of a failure, right? So think like hard drives. You can have hot spare hard drives in a machine if it has open slots, and they take over if a hard drive fails, and that's a hot spare. Or you could have several hard drives. You say you have thousands of servers, and maybe you have 100 spare hard drives that you just have sitting, and then if one fails, you would plug it in and replace it. But you don't have them running in all 1,000. You don't want 1,000, but you keep 100, right? Link aggregation or port aggregation is combining of multiple network interfaces to act as one logical interface. An example of this is network card teaming, right? So you take two or more network interfaces or ports, and you combine them together to act logically as one. Increases your total throughput. Automatic failover. If one of them fails, the others still continue. You can do load balancing, and traffic distributions over multiple components or links to optimize performance and fault tolerance. Here's an example. These 3 switch ports are set up to look like one logical switch port for these switches, right? They treat them as one port. So all 3 would have to go bad for this link to fail. Here showing that they've got 2 switch ports going to 2 different network cards on this storage server, and so it's got the added throughput, right, of 2 network cards. Workstation 1 and 2 are able to access the server over network card 1, port 1, and workstation 3 accesses the storage over network card 2 and port 2 on the switch. And so they have more bandwidth available to them. They still limited by the single server in this scenario, but they definitely have more network throughput. Link Aggregation Control Protocol, LACP, right, can dynamically coordinate communication between hosts on aggregate connections. Most of these devices offer similar configuration options. You can do a static configuration, a passive mode, an active mode, right? Then you have load balancer. That's a dedicated device that distributes traffic among multiple computers. Use that a lot for like web servers, where you might have 100 web servers behind a load balancer. But it looks like one web server to the world, right? Think of Google and Facebook, right? They have many web servers, but they all hide behind a single load balancer. Well, maybe they actually have multiple load balancers, but they hide behind their load balancers, and so you go to just one of thousands of web servers, but it's used. Load balancing is used for that. Clustering is a technique of grouping multiple devices so they appear as a single device. Usually accompanies load balancing, but doesn't have to be. You want clustering to occur for redundancy, and for load, sometimes for load as well. A VIP, a virtual IP address, is used to represent the entire cluster. So you access the cluster through the VIP, same as you would on a load balancer. You usually get a virtual IP address on the load balancer, and you access that IP address, and then the cluster or the load balancer actually sends it to the correct machine. Then you have Common Address Redundancy Protocol, or CARP. Allows for a pool of computers or interfaces to share one or more IP addresses, and the pool is known as the redundancy group. So here is that example, like I said, with web servers, right? You have a web server cluster. It doesn't have to be a cluster, but it could just be web servers. And you have the user goes to the internet, hits the server load balancer, and the load balancer picks one of the web servers to send them to, but it spreads the load over the web servers. Distributed switching, right? Centralized controls of VMs, simplifies network operations, minimizes chances for configuration errors, and so you have two hosts with three VMs on each host, but then there's a distributed switch that goes across both hosts, right? So it makes it easy to manage the networks because the VMs are all on the same network on this distributed switch. So it just centralizes our management of VM networks. Backups, right? Copies of data or program files. Decide when and what to back up. Make sure we use data error checking to make sure it's reliable. Verify your backup storage media has sufficient capacity. Know how much backup method media costs. I would definitely also test your backup. You always need to test your backups and verify that it is backing up, and try to restore something from it, just to ensure that it's there. Make choices for storage media, keep backup secured, decide what type of backup, full, incremental, or differential. We'll talk about that a little bit. And develop a backup schedule, establish a regular schedule of verifications. So here, right, so a full backup is you back up everything, right? Then you can do an incremental backup, is what has changed since today, right? What changed today, right? Another incremental backup, what changed today? Incremental backup, right? Once again, what changed today? Then differential backup is this says what's changed this week, but really it's what's changed since the last full backup, right? So that's a differential, and then of course your full backup. So if you're just doing incrementals, right, you need to restore all incrementals, right? You need your full backup, your last full backup, and all the incrementals to restore. Or if you do a differential, you do the full backup and then your last differential, right? So it's just a strategy on how, what makes sense for you. And then, but you can do a full backup on Saturday, right? Incrementals on Monday, Tuesday, Wednesday, and then a differential on Thursday, and then incremental on Friday, and then, like I said, the full on Saturday, something like that. I mean, there's all different ways, but a lot of it, depends on how much time it takes, what's involved, how much storage space you have. There's a lot of factors that go into planning a backup schedule and the type of backup. Network storage, right? So we want to provide hardware redundancy and high-speed access to large amounts of data, right? So data backups, that's you're storing backups of data that are not really accessible. Whereas network storage is accessible data that's used on an ongoing basis, right? Network storage don't necessarily save multiple copies of the same data. Network storage typically it doesn't store data in different geolocations. So if there are multiple copies of the data, network storage technology saves those copies in the same format on the same type of media. So network attached storage is a specialized storage device or group, provides centralized fault tolerant data storage for a network, right? So it's contains its own file system optimized for saving and serving files. It's adaptable. You can store and retrieve data for any type of client. It's easy to expand, so you can add storage without interrupting the service. The NAS server pool of storage space is provided by multiple hard disks, right? It can be configured with a form of RAID, which is a redundant array of inexpensive disks. Four most common types are RAID 0, RAID 1, RAID 5, and RAID 10. RAID 0 is not going to be redundant. It's used for speed. And it uses multiple disks. It writes striped data across multiple disks, and it gives you very fast performance. But if you lose a disk, you lose all your data. RAID 1 is an expensive RAID for duplicating, so it takes a copy. So it takes 2 disks for every set of data, right? So you mirror the disk. You make a duplicate of each disk. You have pairs of disks, and so if you lose a disk, you don't lose the data, but you get half the data storage available to you. RAID 5 is kind of the best of both RAID 0 and RAID 1. It's faster. Then it's striped across the drive, so it's a little faster than RAID 1, and it gives you some redundancy, but it requires 3 or more devices, 3 or more drives. If you lose one, you still have all your data, so that's the benefit of that, but it does cost a little bit more than 0 or 1. RAID 10 is basically you take 4 disks, 2 RAID 0, right? You take 2 of them, you make a RAID 0, and then you take the last 2 and you mirror the first 2, and so you got a copy of a RAID 0, which makes it a RAID 10. So very expensive, very fast. It'll be faster than RAID 5, and secure. You won't lose your data, but it is very expensive. Here's an inexpensive NAS with 4 drives. And here's a graphic image, right? RAID 0, right? The data is striped across the drives. RAID 1 is just, you got 2 disks and they're just duplicates, right? RAID 5 is striped across the 3 drives, but they have parity information so that they can rebuild any failed drive. So, parity information on drive 1 is probably the information from like drive 3. Drive 2 might have drive 1, and drive 3 has drive 1 or 2. So that if one of these drives fails, they can rebuild the other missing data. And then here's RAID 10 on the bottom. You got striped, and then you got duplicates of the stripe. Storage area network is SAN, is a network of storage devices that communicate directly with each other and with other networks. Uses a type of architecture that's similar to mesh topology, which is the most fault tolerant. SANs use one of these technologies: fiber channel over Ethernet, iSCSI, or infinity band. So here is an example of, you have the file servers, right? 2 file servers. You have a fiber channel over Ethernet switch, right? So you've got the Ethernet connections to the file servers, and then you have the Ethernet connections to the storage disk, the actual storage over here, and then the Ethernet clients and network come in and connect to the switch, and they access everything here. But yeah, and it's very, very fast, very efficient, very expensive. A SAN can be installed in a location separate from the LAN it serves. SANs are highly scalable and have a very high fault tolerance, massive storage capabilities, fast data access, and they're best suited to environments with huge quantities of data that must always be quickly reliable. And besides storage, power is another area that we need to manage over our network. Power surges can cause serious damage, right? You need to understand the nature of electrical circuit, electrical components, power flaws like a surge, right? A momentary increase in voltage. Noise is fluctuation in voltage levels. Brownout, momentary decrease in voltage, also known as a sag, and a blackout is a complete loss of power. We have UPSs, or uninterruptible power supplies. They're just battery backups that allow you to function for a limited amount of time while the power is off, and can help. Some of them have conditioners that can prevent undesired fluctuations of power from harming the device. You have a standby that provides continuous voltage to a device by switching to battery when it detects a loss of power, or an online UPS uses AC power from the wall outlet to continuously charge its battery while providing power to the device through its battery. Decide which UPS is right for your network. You need to know the amount of power you need, the power time you need to keep the devices running. Do you need line conditioning, and how much can you spend, right? Testing UPS with your equipment is important, just like testing your backups. You need to test your UPSs. Some manufacturers will provide a warranty and let you test the UPS. Power redundancy, dual power supplies, redundant power circuits. Generators, having a backup generator to provide power redundancy in the fault of a total blackout. Powered by diesel, liquid propane gas, natural gas, or steam. Generators can be combined with large UPSs to ensure that clean power is always available, right? Because it takes time for the generator to kick up and come live. So your UPSs just need to last long enough to get the generators running. If an organization relies on generator, fuel levels and quality should be checked regularly. And there's the UPS and generator, right? You got redundant power coming in, main power distribution. You got your generator, UPS, and then to the equipment. Disasters and security breaches happen, so training and preparing for these can make all the difference in your company's ability to respond, right? So an incident is any event that has an adverse effect on a network's availability or resources. It can be a security breach, infection, or environmental issue. A disaster, an extreme type of incident involving a network outage that affects more than a single system. So your incident response policies, specifically define the characteristics of the event and that qualifies as a formal incident. Define the steps that should be followed. You should be very familiar with the processes. You typically have a 6-stage process. Actually begins before the incident occurs, because you need to prepare and have training, be able to detect, identify that you have an incident, contain, and then figure out what you need to do, and recovery, and then review. Response policy should identify members of a response team. Responsibilities assigned to each member should be clearly spelled out in the policy. Some suggested team roles are below. Disaster recovery. So the process of restoring critical functionality, data affecting more than a single system or a limited group of users. You have a disaster recovery plan, accounts for the worst case scenarios. The goal is to ensure business continuity. You should have a disaster recovery plan in place. You should test this on a routine basis. It needs to be continually updated. You need to know who needs to be contacted in the situation, how do you restore services. All of that should be in your recovery plan. Contact names, details on what data servers are being backed up, where the backups are kept, details on network topology, redundancy, regular strategies for testing the disaster plan for managing the crisis. Then having a comprehensive disaster recovery plan lessens the risk of losing critical data, makes potential customers and insurance providers look more favorably on your organization. But having it is good, but you also need to test it on a regular basis. Now, you can, for disaster recovery purposes, you can have a cold site, warm site, or hot site. A cold site is just the components necessary to rebuild a network are available. There's you haven't configured or updated or connected anything. It's not configured, it's not updated, it's not connected. A warm site, the components necessary to rebuild the network are there, and you have some configured updates and connections, right? But it's not 100%, or it might just need data. Things like that. A hot site, components exist and match the network's current state, and it's all configured and updated and connected, and a lot of times has data already. It's just there. It's ready. But of course, the hot site costs a lot of money, but it takes no time to switch over to using the hot site. The warm site, it doesn't cost as much, but it takes a little time, to configure, get things working and set up. A cold site doesn't cost that much, but it takes significant amount of time to get up and running. So what's the important part for you, right? Can you allow a little time? Maybe you have a hot site for one or two critical apps, and then a cold site for the rest, right? All right. Some incidents may require data to be collected in such a way that it can be presented in a court of law, right? So someone must take charge. In this case, and secure the area, document the scene, monitor the evidence, data collection, protect the chain of custody, monitor transport of data, equipment, and create a report. And that is our chapter